Good afternoon. I invite you for lecture 10 from Computer Architecture course, and topic of today's lecture are the functions calls and calling of the services of the operating system. And we start with the RISC-V architecture as the model to show how the functions are called. And then we look how the C code is translated into the assembly language or machine code, where local and global variables are stored in the memory and how they are accessed by a processor. And the final part is about calling of the services of the operating system. Okay, so the first step, for example, you have this source line in your C program, which assigns to a variable A the sum of two other variables, B and C. So what is necessary to do the first? It is necessary to access the variable, so the value from the variable is loaded to the T0 and T1 register, basically some registers which can compiler use to as a temporal variables inside the code. So we read the input values. Then we perform the actual calculation, which is that simple add instruction. And at the end, we store the result to some variable, and in this case we can expect that those variables are global variables and they have only a copy in the temporary T registers. And the actual translation is done through the description of the C language through some context-free grammar, which covers all the expressions which are possible to be written in C language. And this example is completely without the optimization. So in this case, we load the values, perform the calculation, and then store values to the memory, even that there can be some follow-up operation which can reuse the value which is already available in T0 variable of T0 register. So in the more complex code, which is optimized, usually the store to the memory is postponed only to the moment when it is really necessary to deliver the value to the memory. And for the RISC-V architecture, we have seen that we basically cannot encode into the 32-bit instruction the 32-bit address to the memory. So basically we can use only that small offset which has 12 bits, and in the fact it is in the range because it is signed extended, so it is in the range minus 2048 up to plus 2047. So it is relatively small area of memory which can be accessed directly by a single instruction. So for this reason, there is one register which has a role of the global pointer, which points to that area where global variables are placed by the linker. So if we are with those variables in this small range, then it is relatively easy. If we need to access a global variable somewhere else, then we need first to use some sequence of load word and another operation to obtain the address of the variable. Okay, if we go to a little more complex C code, then we have there the while loop, translation, compilation, and again, the first pass finds that there is a while condition body construct. Then the condition expression is somehow translated to some syntax tree which represents the operation. Then the compiler decides that it will be realized by the code where we check for the condition, and if it is not the if it is pass, if the result is true, then it goes to the start of the cycle. Then there is some body of the cycle, and as the startup to this sequence of instruction, there can be used a jump into the middle of the loop before the condition testing. So this way we ensure that even the first run through the loop check the condition. If it is true, then it branch back to the body and executes the body. And this body and condition are translated again exactly the same way as that expression. So basically we need to translate the sequence which evaluates to condition, for example, to T0 register, and then some sequence of operation which will form the body of the loop. And why to bother with translation compilation? We can write even the interpreter, for example, in assembly language or even in some another language, which would interpret directly the C source code. But it would be very inefficient, very, very slow, because it needs to find the text, decode the text, and so on, and then find which operation should be called, and so on. So usually, the interpreted languages, where we have some interpreter in the lower level language or in machine code, which interprets the another higher level language, for example, like in the case of Python, is usually relatively slow. It can be a speed up, so in the fact your Python code is not interpreted line of the text after line of the text. It is first converted to some bytecode, which is then interpreted, but even that interpretation is relatively slow. On the other hand, if you look at the Python code, and if you work with some huge matrices or artificial intelligence code and so on, or for example in this case some video processing and image processing, or NumPy big matrices and so on, then if you use interpreted language only to call the well-optimized libraries written in the C code or some faster code, then you can get even in this case a good result. But anyway, usually we want to use compiled languages for those part of the code where the throughput is critical, and we can use C, C++, Rust, Fortran, Pascal, and so on. And even, for example, Java and such languages are first translated to bytecode, but at runtime they are translated to the native code. So on some parts, Java hotspot and so on. So we usually do not directly execute those languages in C, and we translate them to the machine instruction. And if programmer has no idea what is result of the translation, then you can do a lot of problematic construction in the code. If you really fully on the optimization and do not understand even some side effects and some undefined behaviors, you can have problem. For example, if you define a local variable, automatic variable, as an array which will need 100 megabyte of the size. Then in the single thread application, maybe it can work sometimes on the Unixes. On the Windows, I think it would be a big problem. But with multi-threaded application, it would not probably work because there the stack areas are limited for each thread and so on. And if you do not understand that, for example, recursion can lead to the stack overflow, you can be in troubles and so on. So to have some idea how the code is translated and what is the function in the machine code, how it corresponds to the C source, then you will have a homework number 4, where you get a listing in the RISC-V assembly and in the x86 and MIPS assembly of the same code written originally in the C language, but you will not have the sources. And your goal will be to find what is the function of the code and rewrite it in the equivalent C code, which will be compiled and compared to behave equivalent way to the listing which you get. So, if we look how the function call is translated in the C, then we have there some simple function to add two numbers. And we need to find and decide how we will pass the arguments to the function, how it will return the result, and how to ensure that if you call the function, we can continue in the caller, that function which calls this function, on the next instruction. And all this is defined by the application binary interface, ABI, which is specific for a given architecture. So at this moment, we are switching from the C, which is architecture independent, except for some limits and some details, but basically you can write, if you know how to write it, you can write the code which can run on big endian, little endian, 32-bit, 64-bit, 16-bit, even 8-bit processor, and it can be a same source. I have written a lot of such source. So it is no problem. But at the moment when we go lower, then it has to be translated to the actual ABI of the, which has been defined usually by the architect of the given architecture, or sometimes by the compiler architects and so on for the given architecture. It is even possible that you compile the Kali, the library or something on different computer than on which actually the application then runs, or core, it depends. So for example, in your case of MZ-APO boards, you compile on the x86, but code which is for the ARM, for the target. So it is necessary to ensure that the libraries and the code matches. And usually that information, what ABI has been used for a given fragment compilation unit, is stored even in the object file. So if you try to combine incompatible modules, then you get some error and so on. And now we look at the example of calling convention for a RISC-V. And in this case, it is easy because the registers are divided not by the hardware, but by the definition of the programmers and architecture designers to those symbolic mnemonic names. So the registers which are marked as A are argument. So those 8 registers can be used for up to 8 arguments, which are used and passed to the function. If the function is expecting more than 8 arguments, then, or some of them are some large structures and so on, then those additional arguments are passed over the memory. So there are some rules how to pass it over the stack. And the result of the function is stored to A0 register again, usually on some another architectures which do not overlap the registers to return value with the argument registers. This one is called V0 and V1, value 0, value 1, but in this case the function returns the value exactly in the same registers as are first and second argument. And if it is if it doesn't fit into the 32-bit register in the 32-bit case or 64-bit in 64-bit case, then A1, the second register, is used to store the rest of the return value. If the value exceeds the capacity of those 2 words in those 2 registers, then memory is used and caller is passing hidden pointer to the memory area where the result should be stored. So basically in such case all arguments are shifted by 1, that the first argument is in the A1 and A0 points to that memory location to which function should fill the result. So in this case call it, so that function which is called returns the result this way. So there is an example. So we have there some function which should provide some permutation, for example. It has 2 input arguments and returns a structure which expects that it needs to store probably for 32-bit system 16 bytes, because it is each of those numbers is 4 bytes, so 16 bytes. But in this case, the calling, which would look something like this, is in the fact translated as the function which doesn't return any value in A0 and A1 and stores the result at the address which is provided by A0 here. So basically it is what happens automatically. For another case is, for example, if you call a method, virtual method of some or method, non-static method of some object, then again this pointer is in the fact additional hidden argument to the function. Okay. If we want to return from the function, so for example we have there that function add2 and want to call it once and the first time and second time. So basically when we jump to this location, then there is a body of the function, and then where we should return? Should we return there or there? We do not know that at the compilation time, because for each invocation it is necessary to specify a different address to which we should return after the function is executed. And in the case of the RISC-V processor, one of the register which is called return address register, it is mnemonic name, but in the fact it is the register X1, is used to store the address. So basically we need to set the X1 to point after the instruction which calls the function. Then we call the function, and at the end function can use this address where it should return that the code can continue after this addition at 2. It would be a more instruction. We need to store the correct value to x1, then to call or jump to the start of the add2 function, and so on. So because we see that this combination of operation is required quite often, then we define some instruction which allows to provide this functionality. So the first is jump and link. That link means that it links the return address register to point after the instruction which invokes the call. So we start this operation. We can specify which register should hold an address of the instruction which is following the jump and link. So basically this is where we want to continue when the subroutine returns. Then there is the address where is the start of the subroutine. That address is stored in this part of the instruction, in those top 20 bits which are used for the jump immediate operand. But there is some change in the encoding, that the bit which corresponds to the least significant bit after the addition is in the fact not useful, because we require that all instructions start on even address. So this bit is reused as the bit which corresponds to the bit 19, and bit 20 is the sign. So at the end we have 21 ability to use something like 21 bits with the sign which represents the ability to branch in the range plus minus 1 megabyte against the actual location of the program counter. So we can branch directly with this single instruction in this range, and this specific instruction has that additional value that it stores the address of the following instruction, so in the fact the PC plus 4 to the destination register, and if it is not specified, if you write only jump and link and the address, then it is stored to the x1, or you can explicitly say x1, and this is in the fact the calling the function. If you want only to one directional jump to some location, for example in the loop and so on, then you can use exactly the same instruction, but specify that destination register is x0, which is fixed 0. So basically it can be used as the discard, and in this case we jump only to the given location, and we can use instruction J for this purpose, which specifies that the destination is x0. Sometimes you want to jump to some subroutine which is specified, for example, by the pointer. If we have a virtual function, then we read the virtual function pointer and need to jump to the start of that virtual function. Or sometimes you want to return from the subroutine. So for this reason, we have there another instruction which is jump and link. And if we want to use it as the branch to or jump to the subroutine, then we specify with RD that it should store the next instruction address to the x1. So it works same as a jump and link. Or we can specify with jump relative or jump register, that we only want to jump to the given location, but do not want to modify a return address register or some another register. And this combination where we jump to a return address is in the fact equivalent to the return instruction from the function. And what we need to do with our processor to ensure that we can realize those operations. So for that jump and link, we need the operation when we can combine the RS1 together with some immediate operand. So it is, in this case, we get. So this is, so we need to add there another multiplexer which allows to combine, because it is PC relative, it allows to combine the value with the program counter or with the register. So we have those two options. For the jump and link relative, we will use directly the value from the register, add the value and use it for something, or we can use a program counter value in this location. Then there is a need for the other multiplexer, because in the case that we want to store the address of the next instruction, so it is that PC +4, this one, to the register, then we need to specify that the destination register is X1 or some another register, which we can specify there, this way, and then say, okay, the value of that register is not provided by the arithmetic logic unit, but it is provided by that PC +4, so basically the next instruction address. So it is what we can do. And then the last thing which is necessary, we have there that ability of the relative branches, which allows to branch relative for the conditional branches relative in that range ±4 kilobytes. But in this case, we do not want to use this small range, but we want to use a real result from the arithmetic logic instruction, from the arithmetic logic unit, to specify the next address. So we need to do those modifications to our processor. Okay, so please go through the diagram, try to understand how the instruction is decoded. It specifies what will be the RS1 register, RS2 if they both are used. We have there that option that immediate value is provided by the second register or by immediate operand. Then we have that output from the arithmetic logic unit, which can be used for address to the data memory. In such case, if we want to write, then the second register is used as the data which are written to the memory, or we can use the address and read the value from the memory. Here we see that there is that problem with the hazard when we try to modify the register. If this wire specifies this signal, that we modify the register which is read by some of the following instruction here. So in such case, we can forward there the value. For example, even we can forward even that result of the return address register, or that register which is changed by jump and link or jump and link register, we can forward it. So it is not necessary to stall on such instructions. You have the third homework, so you should know already those stuff where we need to forwarding, where we need to do a stall, and so on. So you can find everything in this picture, or you can try it in the simulator. So there you can see that there is now jump and link instruction, which is in the execute phase. So in this case, we specify that we want to read the value which is forwarded in this way, because it combines x7 is here. You see it is modified. It is used as a base for the branch. So in this case, we know that that modified value is available there, and it goes through this forwarding there to the input of arithmetic logic unit. So please try to locate those things, and you see that there is the result address, which will be used for in the next cycle to specify where we should branch. So in this case, output of arithmetic logic unit specifies the address where we want to branch. Now it goes through this signal to the input of the program counter, which doesn't advance to the next instruction, which would be provided here, but it doesn't advance to this location, but instead it branches to the new address. There is one significant problem, that we modify the address and at this location and the memory stage where we should branch and continue with the reading of the instruction, but in between already there is fetch one instruction, one is decode, and one is in the execute stage. So basically after the branch, in this model of the processor, we need to flush all those three instructions. It is, again, I am repeating something which you should know already, because we have a branch predictions and so on. If we have a branch prediction, then in such case, if it finds that it is better to fetch the instructions after our branch instruction from the target of the branch, then it tries to fill those stages by the instruction at the destination address of the branch. But on the other hand, at the moment when we find that we do not branch or branch to a different location here in the memory stage, then again we need to flush the instruction which are before. Yes? But jump and link register is not, because it depends on, it is for 100%, you know that branch history should specify, okay, this is the branch, and there in the fact we do not need to store it in the branch history, because we know it will branch for sure. But problem is that the branch target buffer can depend that you are, for example, on the same instruction, which calls draw the shape. But if the object which it should be drawn is the circle, then it branches to the method draw circle. But in the next run through the cycle, for example, it can branch to the draw the triangle or draw the rectangle, so on. So you can see that if you do the object-oriented programming, it can confuse a processor a lot. So even for such case, if you can sort the object that first come all the circles, and then all the triangles, and then all the rectangles, then you can get a significant speed up, because we have said that the predicted branch can correspond to something like 100, 150 instruction slots which are lost. So it can be 100 times, for example, slower. Okay. What to do if the function body calls another function? So basically, if we have some call graph where we have one function calling another function and so on, then, okay, we need to prepare in our function, which want to call some another function, we need to prepare the arguments which we need to prepare the return address and so on. But how we can solve to keep the arguments over the call of another function, because another function has its arguments, our function has its arguments, and if we modify them to call the function, and even the function has a right to rewrite those argument register, then we lose our arguments and cannot compute with them after the another function is called. So we need to store somewhere those arguments which would be overridden by the calling of the another function. And for this store, there is use so-called activation record or function frame and a stack. So basically, because stack is structure which has big advantage that it is very easy to allocate and release location. In the fact, stack usually today on most of the processors grows down, and the allocation is only to moving the pointer to the top of the stack. So work with the stack is very fast. So if we have some hypothetical push operation which is available, for example, on x86, but not on the RISC-V, then if we push the first argument, then we push some another value, and so on. And then it is in the fact last in, first out. So when we do the first pop, we get the element which is top level element on the stack, which is on the bottom on the image. Be careful that basically it is vice versa, but it is same what like programmers usually draw trees which has root on the top. So okay, do not mind that it is going vice versa. So basically, if we do a pop, we take the this third argument. Then if we do another push, we put there the 4, and again the following pop takes the 4, and the last pop takes the 1. And how we can implement this on the RISC-V processor? In the case of RISC-V processor, we have a definition in the application binary interface that the stack pointer, that pointer to the top of the stack, which points there and there on the top stack element, is stored that value in the register X2, and in the fact the push operation is equivalent to the decrement by 4 on the 32-bit system. On 64-bit system it would be by 8 of the stack pointer, and then storing some value to the location. If we want to, yes? Because the addresses are going down. Stack is growing from the top of the memory. There are some reasons for this, because usually heap is growing from the bottom to top. So basically, that space is from one side used by stack, from another side used by heap. So typically, and for example, GNU compiler is prepared even for the top growing stacks. but I'm not sure, I do not remember architecture which used the vice versa order. There has been some in the past, but I do not remember them already. Okay, and if we want to restore the value, then the last value of SP points to the last element. So we do the steps vice versa. We load the value and then increase the stack. And there is another reason why we want to have the stack organized this way, that the arguments are organized in the more natural order. We will see that later. So there are more reasons why to leave the stack growing down. Okay, so what can be stored in those stack frames? There can be stored, for example, a return address and arguments which would be later overridden, clobbered by some calling of some function in the body of our function. We can use a stack to store function local or automatic variables, which lifetime is limited by the body or even by some block. And there is some specification that ABI forbids to modify the value of some another registers. So basically you need to ensure that when the function returns, the state of the registers, values in the registers, which are denoted by the S, which means the safe, has to be restored to the original state of the which has been found when the function has been called. So if you want to use some of those registers in your code, then it is necessary to first save them on the stack. Then you can use them for the local variables. They have advantage if you compare it to the T, temporary, that they are not overridden by the calling of the functions, but in this case it is your task to ensure that you return with the previous values. Sometimes the register S0 is used as a special frame pointer inside the stack, which is necessary to keep the frame pointer if you want to use a stack for some local dynamic allocation. I will get to that a little later. So basically a frame pointer points to the fixed stack position, usually that one which corresponds to the stack pointer at the time of function entry. And it allows during the body of the function to reserve more space, for example, for the arguments to some other function and so on. So basically to move the stack pointer, and which can be in the theory compensated that you know how the offset to the variables and arguments and so on change during the execution of the function. So this is not yet 100% necessary to have a frame pointer, but where you need to have a frame pointer is if you want to use a alloca call, which is automatic allocation on the stack. I'm not sure if somebody knows that this function exists. Who knows that the alloca function exists? Nobody. So it is the function which allows you allocate very efficiently and fast memory, which is released at the time when you return from the function. Because at that moment, the value of stack pointer is reload from the frame pointer, and basically this area which has been allocated by those allocas on the top of the stack is freed automatically. This alloca mechanism is used as well in the case if you have variable length array in the C as a local variable, which is allowed. In C11, you can have some local variable, which is, for example, int array, and there can be the A1, which this A1 is some argument to the function. So in this case, you allocate the array which is allocated on the stack. Those S registers are different in the respect to the A and temporary registers. So we have the categories. Basically, S as a safe, T as the temporary, and A as the arguments. Arguments register, when they are not used for the arguments, can be used as the temporary. We get to that later, but anyway, I start with this description. And safe registers are another category of registers, which has advantage that you know that if you call the subroutine, it will keep the value. So for example, if you have some loop counter in some for cycle in which you call the another functions, then in this case you can store your loop counter in the one of the S registers, and you do not need to save it before each call of the subroutine to memory and then restore it, because you know that the function which you call, some another callee, will not overwrite your value. But it has that disadvantage because it has to be preserved, that if you want to use it, you need to store it first to the stack in your function. So there is, which is, now we get to the whole definition. So basically, there are those argument registers. There are quite a lot of argument registers reserved in the ABI of RISC-V. So up to 8 32-bit values can be passed through the registers, and those are input argument, and it is allowed to do what you want with them in the function. You do not need to care that you modify them and then return from the function, because they are so-called callee clobberable. You can clobber them, change the value. The first two are used even as the return value registers, so in the fact as V0 and V1, but it is not used with this demarking on the RISC-V, and those are those first two of argument registers. Then there is that return address register, which has that specific purpose to store the return address. But in the actual instruction encoding, it is explicit, so it is possible to define the ABI which use a different register as the return address. But it is not a good idea, because it would make problems to some predictions and so on. So basically, if you use the functions, return address register should be mapped to the X1. And okay, there is one register missing. We should say that X0 is in the FAG0 register. Okay, fixed 0. Then we have there some set registers which is specified as the temporary. So those can be used for some local computation and so on. But if you call the function, you are not guaranteed that they will keep their value. Then there is that set of the saved registers. And for those, it is necessary to ensure that you do not modify. So basically, for the return address, again, it is the rule that when you return from your function, then there will be exactly that value which has been in the register when your function has been entered. Then there is that stack pointer, which allows to work with the stack, allocate the space on the stack. It is mapped to X2 register. And then there is that global pointer, which points somewhere in that area of the global variables, because we are not able to address in a whole 32-bit range easily. So this points to that area of global variables. And there is even reserved one register which is called a thread pointer. It is for more advanced description and discussion for the operating system, but basically it is pointer to some thread local storage which is used sometimes in the multi-threaded programs. Okay, as for the actual data type, how they are passed. So if we have a character, short, integer, long, and float, and even pointer, then on 32-bit RISC-V architecture, each of those arguments will occupy a single A register. So some AX register for each of them. If you have a long, so 64-bit integer or a 64-bit double value, then in the integer-only processor implementation, those will be passed through AX registers as well, but in the pair, because 64-bit do not fit to the 32-bit register, so those are in the pair. And even if you have, for example, char and then double operands, then there will be a A0 used for char, and A1 will be skipped, and A2 and A3 would be used for the double, because there is requirement that first of the pair of the registers has to be an even number. This is necessary that when you store it to the memory, then that they are well aligned and so on. If we have small structures which are passed by value, then they are copied according to the above rules into the registers, or sometimes they are even packed into the registers, so you can pass a structure through the registers. If the code is compiled with the floating point extension for the RISC-V, then the float and double arguments are passed in the floating point unit. So registers F10 to F17 are used as the argument registers for the floating point operation. So in this case, you can have up to 8 operands even in the floating point. If the operand or argument do not fit into the given register, then the rest is passed over the stack. So we can use the stack to store more arguments. And there is a rule that the stack position is aligned to the 16 bytes, because it allows a faster load by whole cache line, for example, for the case of the multimedia registers load and so on. So for this reason. Okay, so when we need to store the S0 to S11 to the stack, or some of them. So who is for A? No, because if we call another function, then for safe registers, it is defined that they would not be clobbered. See? If they are used for the local variables, because in such case, we need to first store them to the stack, then we can use them as the local variables, and we do not care about the calling of some other functions and so on. And at the end, we need to restore them from the stack to return with the previous state of those. So the correct answer is C in this case. Okay. And what about the A registers, arguments, when they will be stored onto the stack? Yes, again the C. because if we want to use some argument, or maybe we can use it even for some local variable, then if we call another function, it could rewrite the value in those registers, and if we need it after the call to the subroutine, then we need to preserve them over the call of that subroutine. Okay, and now if we have some function, then this is the simple case how we can call the function with 4 arguments. And as you see, for some reason, it is started from the A3 and fills the arguments to A0, and then jump and link with the return address set to some function add4. So it is easy. And add4 can add those 3 registers together and put the result to A0 and return. So it is easy. At the moment when we have the function which is called with 10 arguments, then the thing starts to be a little more complex, because we need to store the values first on the stack, and we need to have some space on the top of the stack ready for this. So for this reason, but we do not take care about it. We expect that at this moment we have some space on the top of the stack. There is pointing stack pointer, and then there is some space on the top of the stack, and we store the argument 9 exactly at the position where points stack pointer, and 10 to the next location, so SP plus 4. And the rest of the arguments are stored to the registers, and then we call the function add10. And function add10 can add all those A registers easily, and for those arguments, last 2 arguments, it needs to read them from the stack. So if we look at the translation of some simple function, then, for example, in this case, it creates a space on the stack that it reserves a space of 16 bytes by this subtraction. This SP is that previous SP of that function which calls our function. Now the SP points to this location. And then if we need to use some local variables, then we have there the space for 4 local variables which are of the size of 4 bytes each. And at the end of our function, we need again to restore the previous state. So we add the 16 to the stack pointer, and to return from the function, it is enough to do a jump and link to the X1 register, which holds that return address. And we can replace this with the simple instruction, which is translate exactly to the same code, but it is easier to write, which is called return. Now, if we look at that function which has 10 arguments, then in this case, we need to store or some more complex function. Then we create the space on the stack in the function, and then we store the previous return address to that location. So basically, if you see, we have subtract the 48. So if we add back 44, then we are at this location exactly below the previous stack. Then we put there a return address. Then we can use some space which we have built the space here to save the save registers that we have released them for a free use inside the function. And then we have there a space for 4 local variables. For example, in this case, one of those local variables is only character, so it is in this case allocated at plus 15, so exactly there in the last part of this offset 12. And if we want to access the arguments, then we need to access them as a stack pointer plus, in this case, 48. It is that argument 9 and 52 offset, which points to the argument 10. So this way we can use a stack pointer. We have create the space. In the fact, again, the initial address of the stack, they are those arguments at the offset plus 0 and plus 4. But because we have allocate the space on the top of the stack, then we need to access the argument with just offset 48 and 52. Okay. And in this case, we have stored even the S0, and we usually can use that S0 as the frame pointer, which simplifies the addressing of the stack. So usually the frame pointer, that S0, points or keeps the value of the stack at the function entry. And S0 is used as the frame pointer, and it is called safe, so we need, in our function, which starts, we need to store it in the function prolog, the previous value, because it is non-globalizable, we cannot modify it, we need to return it with the same state as was at the start. And we need to restore it at exist. And what is the advantage when we use a frame pointer? It is easy because it points exactly at the first, after or below the first argument, so it is quite easy to find the first argument, because if you look, so there was the original SP, I think that it usually moves one down, so there would be a frame pointer. So plus 4 is the first argument, plus A is, no, not first argument, that first argument which do not fit into the registers and so on. So it makes it easy and allows us to change the value of the stack pointer without need to take care about a different offset to the arguments. We can use at this moment the stack pointer as the way to allocate the space on the top of the stack, and at the end of the function we reload the registers from that area where we store them, those safe registers, and then we can reset the stack pointer to the location of the frame pointer. So this is the mechanism how it is used. And in the case of that allocation space to call another functions and so on, it is not strictly necessary to switch to frame pointer. But at the moment, when you have those variable length arrays or use that automatic allocation, then in this case you have a problem. And the frame pointer makes debugging much easier, because if you look at the location of the frame pointer, you find the pointer to the previous frame pointer and so on. So this way you can do very easily so-called stack unwinding. So analysis of the stack in the debugger, and where it is very important stack unwinding is if you want to process the C++ exceptions without the complexity of long jump and so on. There is some another mechanism which can be used to resolve the exceptions in the C and C++, but that stack unwinding has advantage that it has zero overhead in the case that there is no exception, and if there is exception, then you use the tables which informs how to reconstruct the stack to that point where there is a catch directive, where you catch the exception and want to process it, because basically you have some function, that function calls in try except or catch, and then you call some functions, and then there is some function which result in throw, and then you need somehow undo those allocation on the stack and restore the state and so on, because you can have there the catch and retro and so on. So all this is done through this stack unwinding. On the other hand, there is a disadvantage when you use a frame pointer, that it slows down a little the program, because you need to store the previous value of the frame pointer to the stack and entry of the given function, and frame pointer allocates one register which could be used for something better maybe. So if you want to enforce that the compiler doesn't skip the allocation of the frame pointer, this is default today, so it is omit frame pointer, which means if it is possible and if compiler thinks that it worth to be done, it doesn't set up the frame. And if you specify no omit frame pointer, then it means that it has to allocate the frame pointer during each function call. And there is a case of prolog when we have the frame pointer set up. So you see we allocate the space 48 bytes. In this case, there is a stack pointer, and we move it by 48 bytes down. Then at the value plus 44, we store a return address, and plus 40, we store the previous value of the frame pointer. And a frame pointer in this case points, okay, it depends, but usually it points to the same address as the stack at the entry. So basically we know that it points to the first argument, and if we subtract the 4, we get return address, and subtract the 8 and get the previous frame pointer. Be careful, on x86 it is typical that frame pointer points to the location of the frame pointer in the stack. It is a little different, but okay. So this way we have set up the frame pointer this way, because now we have the frame pointer as 0, which points to the previous location of the stack. We can very easily access local variables and the arguments and so on, because all this is relative to that frame pointer. And at the end of the function, we can restore the state, and usually usually we start with the load war against S0. We should use this against S0. In some cases it is against SP, but it is still not the fully dynamic function, because if the function calls the alloca, you do not know where the stack pointer at the end is. So in this case, you need to use S0 as the pointer to restore the rest of the registers, or you need to reset first the reset stack pointer to S0 and then to restore the rest. So basically this is a little simplified, this case still. Okay, and now we can get to your homework. For you have already generated the task for everybody of you, which is in the form of the zip file, where you have a listing of unknown C code translated into the RISC-V, x86, and MIPS machine code. And the first task is to analyze that there is some function which is called the subroutine function, and to analyze how many arguments and what is the purpose of those arguments. In the fact, it is tested only if it is something in the range of integer values, or if it is pointer to something else. So this is what is checked in your submission. And the arguments are filled before that analyzed function call. Be careful that those A registers can be used even as a temporal variable. So if the subroutine is using the A register which has never been filled by the subroutine, then it has to be an input argument. If it is first written by the function, then it is a local variable with no connection to the calling function. Then you need to find what is stored into the A0, or maybe even A1, but usually only in the A0, when there is a return from a given subroutine. So it would be a result from the subroutine. Typically, you can find some prolog here, but the functions are compiled some with omit frame pointer, some without it. So if there is a frame setup, then you will find there some such sequence which stores the previous state of return address and some safe registers to the stack. And in this case, if some S variables, S registers are stored on the stack, then they can be used as the local or automatic variables inside the function. In this case, yes, those locations can be used as the automatic variables. But in this case, yes, S0 and 23, so basically some such area can be used for something. Then those S0 and up to some S, for example 4 in this case, when they have been stored, can be used to keep some values even over the function calls and system calls. And if you find that your function doesn't contain the subtraction, so modification of stack pointer, then it is simple function which doesn't use a stack at all. And okay, automatic variable for those are used those registers typically, but even those S registers sometimes can be used for them. Okay, if you look to the whole process address space organization, then in the case of 32-bit system, we have there FFFFF, there is a 0, 0, 0, 0, and there will be something like C 0, 0, 0, 0, 0, 0, 0, and B, F, 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 and so on. So basically, this is the limit, typical limit of the address space of the user task, which has its own separate virtual address space, 4 gigabytes for a given task. But it is not covered whole in the memory. You already know that virtual memory doesn't in the fact exist as a whole, only the part is mapped to the physical memory. And you see that stacks is typically allocated and set up at the start below that limit, because this part of the address space is reserved for the operating system, where the operating system is mapped to each task. And when you invoke the system call, then the execution is transferred to that protected part which you cannot read and write and execute directly. But then there is the stack which grows usually down. Then there is a area which is used to map shared libraries. Then there is the area where we have actual program code. In this case, it is called a text. For historical reason, it is the text of the recipe. So basically the text of the program that we have a global data, which is initialized data by some values. Then block starting by symbol area BSS, it is historical name, but for the C programs, it is for variables, global variables, which do not assign the value in the code. So basically, those are in the C, even that they are called uninitialized. And in the case of the C, it means that they are initialized to 0, which is the rule for the C. And then what is left here, the rest of the address space is used for the heap to allocate the memory by the malloc and so on. And usually program doesn't start at the address 0, and there is some space reserved which is used to catch the error, the reference, if you have a null pointer or some offsets against a null pointer and so on. Okay, some of your tasks can have a global variables. So if there are global variables, then those are the variables which are defined outside of the function or as a static inside the function. And global variables are mapped into the final executable into the data section, if this is initialized, if it is uninitialized or initialized by a 0, then into the BSS section, and you find that it is a global variable in your listing that, or maybe some string or some text and whatever, you will find that something like that is used because there is in the listing a section which is called my data, and in the listing you find that there is address where it will be stored in the virtual address space. Then there are individual bytes in the hexadecimal representation, and then after the 16 position, 16 bytes which are printed in hexadecimal, up to 16 bytes, there is ASCII representation of those bytes. So for example, if there is some text file name or something like that, you can find them in the ASCII. And in the actual code, the access to the global variables is realized usually with some sequence which first prepares upper part of the address of the global variable, then it added together with some lower part and then access the actual value. But sometimes it can be a relative to the global pointer as well. So you will find it. Okay. So now yet another quiz. If we have this function which has one argument and one local variable, where are those variables or those values allocated in the RISC-V case? It is the data section which is allocated. We have seen the data section here. It is, you have text, actual program, then the initialized variables which are stored in the data section, and then there is a BSS section, and then the rest is left for a heap. Yes, both can be in the registers. So basically, but not both in the stack, because A is in the register. So but it can be on the stack or in the registers. So basically, this holds. It is argument. Because it is local variable, and if you want to have a recursion, then you need a new instance for each of the function which in the recursion. So basically, the automatic variable, you need to allocate a new space. It is only during the lifetime of the function, but even when you call the another function, because it is still lifetime of my function. So if I have the function which calls another functions and so on, you have that call tree, then basically if, for example, it is used in this location, there is the I as the automatic variable, then you need to ensure that it survives over the whole calling of those all, but when you return back, it should be deallocated. So basically, but it works quite well, because during this call to the function f, basically you allocate the space on the stack, for example, or you use S registers, which anyway needs to be stored to the stack. Then you use it for the I, and then you call the another functions, and you keep your you keep it in the stack, or somebody else who reuse the S register keep it in the stack. So basically it is, and you do not need to take care about some complex deallocation, like it's the free from the heap, which is quite complex. But on the other hand, if you are writing, for example, drivers or something, then in the operating system, usually you have very limited space for the stack. In the Linux kernel, you have only, at the start it was 4 kilobytes, now you have 8 kilobytes for the stack for the task inside the kernel. So in this case, even for some more huge local stuff, you need to use the allocation of the memory. So it is, but in the user task, okay. Yes, and now we get to the today very popular problems with the security, and it is a stack overflow problem in this case, because if we have, this is example which you can write yourself, if we have some way how we can insert the code, or for example we know that there is some code in the given process, which for example allows to gain you some access to the operating system. For example, there is probably somewhere the system functions, which allows to invoke the shell. So if you are accessing a web browser and you can force the web server to access to call, instead of processing your request, HTTP request, you enforce it to jump to the function in the library which starts the shell and ensure what should be started there with the shell, for example, even the command line. Then basically you can get the access to the system shell at the system running the browser, which you probably do not want to allow to the users. And there is a problem that if you allocate this, for example, this small array in your code, and allow to access arbitrary location in that array to some function which is called from your function, then what can happen is that a given location on the stack would be rewritten, because if you access the array, then there is the array, but if you index against this array, then C basically doesn't prevent you to use even indexes which are out of the range of the given array. So if you use this offset, in this case it is 11, and somehow enforce through some command or some misbehavior of the code that you modify this return address, then when this given function tries to return from itself, then instead of returning to the caller, it returns to the virus function in this case. Okay, it is a simplified example, but basically it demonstrates how the Stack Overflow can be exposed. And for example, very nice way how to do it in the C is if you call the C function getS, because it has a pointer to some string, but doesn't check the limits of it. So basically, in such case, you expect that you get, for example, line of the maximum length of the 20 bytes, and somebody writes a little more, and that more overrides here that return address and some arguments to some another function, and you are done. Basically, you gain the access to the system. It is called a return address programming, and it is a big problem. So, for example, that getS function is, I think that it is deprecated, and maybe from some versions of the C library it's already disabled, because it is security problem. So you should not use it, and you need to check such thing. Okay, sometimes you want to work with the functions which has variable number of the arguments. So they are called variadic C functions. Again, has somebody used some variadic C function? And who have never used printf? Never used printf? Yes, you have used it. So basically, everybody from you have used a variadic function, because printf has the format string which specify what are the other arguments after that format. So it is a variadic. And if you want to write a function which is variadic and calls a variadic function, then it is even more complex. But anyway, there is a simple function which is simplified example that should sum n arguments, and the first argument is the number of arguments which should be summed together. So how we can access those arguments? First, we set up this special variable argument list with this variable argument start. Then we can access, in this case we know that the n arguments, following arguments are something what we want to access, and then we can go through those all arguments and sum them, for example, and at the end we should stop our iteration over the variable argument list, and in today's systems it is critical. In the older system it was not so big trouble if you do not end the iteration, but today you even cannot copy the argument pointer. It is necessary to use a VA copy if you want to copy this list to be able to iterate again next time over the list. And this is how you can call. So basically, in this case, you say, okay, I want to sum 8 numbers. You write them this way. Okay, it is mostly nonsense to write the function this way, because you probably would provide a pointer to the array and sum it from the array. But it demonstrates that it is possible to write the C code this way. And for that printf, for example, it is very convenient that you can have variable arguments with variable type, and you can, for each of those arguments over which you iterate, you basically say what is the type of the argument, again this pointer, and then it moves to the next one. So next time when you use the VA arg preprocessor macro, then you get a next argument with the type which you need to specify. So if we look what happens in this case, then in this case, to allow the easy iteration over the arguments, it is solved by the RISC-V and the GCC compiler such way that it stores those arguments. So first, okay, in this case, first 7 or the argument, the A0 is the n, so it is not stored, but at the time where this VA start is invoked, then in this case, it ensures that for all other arguments, they are stored to the stack, and then those following, 8, 9, 10, and so on, are stored on the stack anyway. So you see that the calling convention is the same, and that in the fact the calling caller doesn't need to know that it is a variable argument function and stores the data correct way that they can be accessed. For x86 it is little more complex, so there is necessary to have at least the prototype. If you do not have the prototype for the function, then it needs to add unnecessary additional information to the register A, I think, AL. So this is better to have the prototype for the functions anyway. But this way it stores the argument, and then it can access the actual location through this sequence where it takes the stack pointer and access the actual locations on the stack. So it takes the, and in the fact, this is the argument pointer. It remembers the value in A4 and takes the integer from it, and it advances it again, the argument pointer to the next one. That next one invocation of this macro will give you a next location. And at the end, we need to restore the previous state of the stack pointer. So there is exactly same move of the stack to the previous value. Okay, now if we look at the operating system protection, then we know that thanks to the separate address spaces, memory content, we cannot override the other process memory, and to ensure that the user cannot directly change, for example, data on the disk or something like that, we cannot allow the direct access to the hardware to the user task, usually. You have seen that on the MZ-APO we can remap some part of the memory, and it is possible sometimes remap some specific peripheral to the user task in some specific condition, but a lot of care has to be taken to ensure that the user cannot do something above his hair or right. So so basically, the basic rule is that process cannot freely and directly access the hardware. So for each access of the hardware, we need to ask the operating system to process our request, handle our request, and the operating system provides those services which are run at the privilege access. And they provide them to the processes in the form of system calls. And if we compare it with the function call, in the case of system call, we cannot control where the execution will continue from the user task. Basically, user task only invokes the system call, and it is given by the setup of the operating system, which set up some mechanism how to handle those requests. And because we cannot have in the fact multiple functions. We can invoke only the system call, but cannot say at which address and so on it should be started. Then we need to multiplex that single system call for multiple services. So in this case, it is done by the system call number. So basically, we invoke the system, and some number specifies which operation we want to process. And the mechanism how to invoke a system call differs on the different architectures, but it is usually some synchronous interrupt or exception. So on the x86, initially on the Unix system, interrupt 80, so 128 decimal, has been used to invoke the interrupt, and it has been then handled as the operating system call. On the newer x86 architectures, there is sysenter and syscall instructions, which allows skip some complexity of the interrupt processing and can go directly to some predefined function, which at the start of the operating system is set to process the system call. On the RISC-V, we have the environment call eCall instruction. I have already spoken about it during the last lecture, and it is in the fact a synchronous exception which is handled by some service routine starting at the preconfigured address. In the case of the RISC-V, it is for the machine mode that MTVEC, or in the system as trap vector register. And the enter of this routine is there is a switch to the system or machine mode, and user cannot change the address where the service routine is called. So basically we return to the same diagram which we have already on the last lecture. So basically there is that attempt, for example, to read the value, to read the data from the serial port. We prepare a read system call with some pointer to some buffer. Then we invoke eCall. At that moment, there is the exception which switches processor to the system mode. System finds, for example, that it cannot find some data which has been previously received from the serial port. So in this case, it blocks and allows to reschedule to other processes to use the processor time for something else useful. Then, when the interrupt from the device arrives, then interrupt handler at that yet another elevated level on the stack process the request from the peripheral. Usually it stores the data somewhere to the kernel memory. Then it invokes, wakes up the waiting task in the kernel, and it finalizes the processing of the data, stores them to the user task address space with some check that user points really to the memory which it owns, not to some another problematic memory, and then it switches back from the system mode to the user mode, and with system read or maybe mread instruction, and the user task continues and reads the data which are provided here. If you look to your homework number 4, then you have there some such simple system calls included in your application. And all this, how we call the functions and how we call the operating system on the given architecture is called the application binary interface. So you know probably POSIX and ANSI and C11 standard and so on. This defines the application programming interface. So how the source code should look like, that it is it conforms the standard, and it specifies what functions should be provided by the libraries and so on. They are provided in the case of C language usually in the form of C language headers, and the API defines not only how we will call the function, but what they return, and what they return in the case of the error, or how they behave. So you can, for example, use this man second section, which is section of the system libraries, for the read. Okay, it is a function, but it is mapped to the system call of the operating system. On the other hand, the application binary interface specifies how it is realized through the registers and the instruction of the processor, and the specification of the application binary interface for the RISC-V can be found, for example, here. And in this case, system call number is stored in the register A7, argument 7. But Linux kernel needs at the most 6 arguments in the registers, so it is not problem that we left the 7, or in the fact 8 argument reserved for the system call number. And then in the case of RISC-V, it is really easy, because exactly the same way as you call the function, you put the arguments to the registers, and then you invoke the eCall instruction. It switches to the kernel, and at the end, when your code continues after the eCall, A0 contains a return value from the operating system. If more data than that single 32-bit value are necessary as a return, then it is solved that you provide through some register the pointer to the memory where the, for example, name of the file or something is stored. So this is a simple application, the Hello World, which you can find even in our RISC-V simulator or something similar. And in this case, we have there the start of the code of our program. It sets the number 64 to the register A7, which is in the fact a system call number, which you find in the tables that it is corresponding to the write. Then you add the 1 or store the 1 in A0, which you know that it is the handle of the standard output of the process. Then the next, so it is that FP. Then there is a pointer to the buffer, which is in this case pointer to this text here, which should be written. It is not necessary to store there the terminal 0 character, because in the case of write system call and function, you need to exactly specify number of the bytes which should be written to the terminal. And then it is necessary to finish the process. So process is finished in this case by exit, function or system call, and it has the system call number 93 and a return value which is 0. And in the homework, you identify in the RISC-V listing the system calls by the eCall. It is very simplified code, because in the reality, you would not find there the eCall, but calling of some wrappers of the system calls and so on in the real code. But we have simplified that it exactly inlines the eCalls into the function. Look at A7 before the eCall is invoked, which informs which function is invoked. You need to find what is set in the A0 and so on registers. Then you can find a corresponding prototype in the standard library. So, for example, if you find that A7 corresponds to the read, then you can rewrite your code in the C as read. And your goal is to rewrite the assembly code back to the C, that it can be compiled again and run same as the previous binary code. There is some problem that for the open and open8 system calls, some of the mode flags are different for x86 and for RISC-V. So in this case, be careful, you need to check for specific architecture what is the encoding. The names of the flags are the same. So if you use file fnctlh, then basically it would work on both, but it is necessary to find the corresponding O flag. And yes, and program is checked by brute, and you can find even the x86 listing. So those flags are probably better to be identified on x86 listing, which corresponds to the x86. And x86 will be the topic of the next lecture, but for the start, you can identify that system call is in the code, in the listing, implemented through the interrupt A0. Be careful that the system call numbers are different between those two architectures, and the arguments to the system calls are stored in those registers on the x86. And more during the next lecture. And okay, there is a quiz again. So we have there a simple function which starts with the static integer. So it is local variable, but which is static. So it is not seen from another functions, but keeps the value till the next execution of the same function. Then there is a local variable integer, and we want to return something. So S is in data section, yes, but it is not announced outside with the label because it is static, so it is in the flag hidden. And the I is on the stack, typically, or in the register. It can be even on the register. But you have no such option here written, so it is the correct SysD. And it is all for today.